My name is Justin Lim, and today I'm talking about our work, finding regions of heterogeneity in decision making via expected conditional covariance. This work is equally contributed by myself, Christina G., and Michael Obers, and is jointly authored with Saul Blecker and Leora Horwitz from NYU, as well as David Sontag from MIT. In this paper, we consider decision-making processes and observe that individuals often make different decisions even when faced with the same context. So, for example, suppose we're in a courtroom and there's a case that's awaiting judgment. To what extent does the decision to either acquit or to convict on this case depend on the judge that makes the decision? For example, Judge A on the left may decide to acquit, while Judge B on the right may decide to convict. Such heterogeneity in decision making is a well documented phenomenon in real life. For example, in a legal context, heterogeneity has been observed in decisions on bail, juvenile incarceration, as well as the use of alternatives to incarceration. In the medical context, heterogeneity has been observed in decisions on surgical intervention, as well as the length of a patient's stay in a hospital. Conceptually, what we want to solve in this paper is as follows. Given the decision-making process, in which cases does changing the decision maker result in a different decision? Answering this question will allow us to identify opportunities to improve decision-making guidelines, which could lead to fairer decisions and better outcomes for stakeholders. In our paper, we use the language of causal inference to approach this problem. And as in all causal inference problems, the fundamental challenge is that we really only observe one judge's decision per case. For example, if we observe Judge A's decision on some case, we don't observe Judge B's decision on the same case. A second challenge in this problem is that we often have only sparse data for each individual decision maker. So we may have hundreds of decision makers with only several observations per decision maker. In this paper, we tackle these challenges and provide a few contributions. The first is that we formalize this problem as a causal inference problem, which is to find a region where the assignment of the decision maker has a large causal effect on the decision. We also provide an iterative algorithm to find such a region together with a generalization bound. And in a semi-synthetic experiment, we show that our algorithm accurately recovers the correct region of disagreement. And on real-world medical datasets, we show that our algorithm recovers variation that aligns with existing clinical knowledge. Now, to begin, let's first define what we mean by a region of heterogeneity. So let's consider an example where there are multiple judges that are making decisions on two types of cases, misdemeanors and felonies. In each case, a judge makes a decision to either convict or to acquit. For misdemeanor cases, some judges, like the first and third judge, decide to convict most of the time, but other judges, like the second and fourth judge, decide to acquit most of the time. So there is heterogeneity in decision making between judges for misdemeanor cases. On the other hand, all judges that see felony cases consistently decide to convict 50% of the time. This means that there is no heterogeneity in decision making for felony cases. Our goal is to characterize the region of cases where the identity of the decision maker makes a substantial difference in the ultimate decision. And here, misdemeanor cases would belong to the region of heterogeneity, and this region is what we want to find. And this illustrative example actually does show some of the challenges that arise when considering such a problem. Firstly, notice that not every judge sees every type of case. The fifth and sixth judges never see misdemeanor cases, and the first and second judge never see felony cases. Another challenge arises when judges don't necessarily see the same types of misdemeanor cases, and these differences may actually explain the differences in their decision making. These two challenges fall naturally into the language of causal inference, which motivates the approach that we take in this paper. And to do so, we formalize what we mean by a decision-making process. And by that, an agent A makes a binary decision Y based on some context X. And the arrows in this diagram refer to the directional relationships between these variables. Now, the fundamental challenge in causal inference, as we've mentioned before, is that we don't observe all of the potential decisions of every agent for every context. And in particular, we don't know what decision a different agent would have made in some situation. So, to tackle this problem, we make two assumptions that are standard in the literature on causal effect estimation. The first is consistency, which connects the potential decision of an agent A, which is y of A, to the observed decision y. The second assumption is no unmeasured confounding, which says that we observe all the variables that influence both the assignment of an agent and the decision itself. And in particular, if we consider this left oval, this pink oval over here, to contain all of the variables that influence agent assignment, and this blue oval on the right to contain all of the variables that influence the decision itself, then assumption 2 says that we observe all of the variables that lie in the intersection of these two ovals, but not necessarily the union of them. So, for example, if there were a variable that influences a judge's decision, but does not influence how cases are assigned to judges, then assumption 2 says that we don't actually need to observe that variable. We've also hinted at this before, but we don't make what is known as the overlap or positivity assumption. And here, what that means is that not every agent sees every context X. Or in other words, not every judge sees every type of case. So, in the absence of such an assumption, how do we still compare the potential decisions of different agents? In this paper, our idea is that we can still measure the difference between a specific agent's decision and the potential decision of a random agent. To illustrate this, let's consider, let's go back to the example that we started with. So here we have multiple judges that are making decisions on misdemeanor cases, and we want to measure the bias of a judge A. We do so by contrasting two quantities. The first is the decision of Judge A, which is to convict, and the second is the potential decision of a random but viable judge. And here, judges 1 to 4 are viable because they do see misdemeanor cases, but judges 5 to 6 are not viable because they never see misdemeanor cases, and so we can't compare their decisions to the decisions of Judge A. Here, we see that the potential decision of a random agent has a lower rate of conviction when compared to the decisions of Judge A. So, we might say that misdemeanor cases belong to the region of heterogeneity, which we denote as S. In mathematical terms, we define what we call the conditional relative agent bias, which is the difference between the potential decision of an agent A and the potential decision of a random agent, which is y of pi of x. And this randomness is assigned proportionally based on the context x. To visualize what this means, consider this diagram on the bottom. So the x-axis here is the context x, and the y-axis here is the potential decision y. The upper curve represents the potential decision of our agent A, and the lower curve represents the potential decision of our random agent. We want to find a region S that is a subset of contexts, and here it's represented as the space between the two vertical lines. And now, the conditional relative agent bias is the expected value of the difference between the two curves taken between the two vertical lines. Now that we've defined how to measure the bias of a specific agent, we go on and define a causal objective that captures aggregate bias across a binary grouping of agents, which we denote as G. This objective is called Q, and it's a function of the region S and the agent grouping G. Notice that Q of S comma G is a weighted sum over the conditional relative agent bias of agents in the grouping, or in other words, where G of A is equal to 1. Now, we make the observation that for a given region S, this objective is maximized by choosing G of A to be equal to 1 whenever the bias of agent A is non-negative on S. This observation allows us to rewrite our objective as a maximization over just the region S, as is represented here in this final objective. Notice that we've also imposed a minimum size constraint on the size of S, which is represented here by the parameter beta. In our paper, we discuss why this minimum size constraint is necessary and also provide a heuristic to tune this parameter in real life. Now, to optimize this objective, we show in the paper that Q of S comma G can be identified as an expected conditional covariance between the decision Y and the agent grouping G. This allows us to identify and estimate Q of S comma G from data without requiring agent-specific models. What this means is that we can apply our methods in settings where data on individual agents is scarce, which is the case in many real-world decision datasets. And in our paper, we applied methods on real-world medical dataset where each doctor has fewer than 9 samples on average. Let's now walk through our semi-synthetic experiment to get a better sense of what our methods look like in practice. So our dataset consists of recidivism predictions using the COMPASS dataset, where mechanical Turk agents predict recidivism based on 5 risk factors. So we generate semi-synthetic data for 2 different experiments. In the first, the ground truth region of heterogeneity is all drug possession charges, and in the second, the region consists of all misdemeanor charges for individuals under the age of 35. We then sample decisions from synthetic agents, which are assigned to one of 2 policies. The base policy is learned on real agent predictions from the data, while the alternative policy has a systematic preference towards recidivism in the region of heterogeneity. Here are our results. The y-axis in these diagrams indicates the AUC, which is based on classifying whether a sample is in the true region of heterogeneity. The x-axis indicates the number of agents in our experiment. And we find that our algorithm outperforms baseline methods when there are many agents and when there are few samples per agent. In our paper, we show that heterogeneity in decision-making can be measured as a causal contrast and show that regions of heterogeneity can be found using an iterative algorithm. Finding such regions can help improve decision-making guidelines, improve fairness, and lead to better outcomes. Finally, please come to our poster and read our paper for more information. Thank you so much for listening.